All right, this is actually section, I believe, 3.4 in the book. And then we're going to go right into example 3.8 after I cover this. So I'm lumping it all into one. The point of this section is to just understand that you can take a system of forces here, like we have force 2, force 1, force 3. They're all acting at a certain distance from this origin, right? This point O. And you can take those and you can combine them, right? So you can move them all to the origin and you combine them into a single moment. So you can basically from F1 and the distance, right, you can get a moment 1. From F2 and its distance, you can get a moment 2. And from F3 and its distance, you can get a moment 3, right? And these moments all sum, and the forces all sum, and you can get a resultant moment and a resultant force, right? So a system of forces can be replaced by a collection of what's called a force couple system acting at a given point, in this case, the origin O. And you can combine it into this, well, you use this vector math to do your work. Your resultant is basically just the sum of the forces, right? Again, these are both vectors, so the resultant is going to be a vector. It's the sum of the forces. The moment vector is just the sum of basically all the position vectors crossed with their respective forces, right? So R1 cross F1, R2 cross F2, R3 cross F3. That's what this is here. And then the force couple system, O, right? You can take that and move it to O prime. And you can define, well, if you add it to the moment of R about O prime, right? You can add it to the original moment, and you can take the new distance, right, S, to the new point, O prime, and you can find the moment about O prime for this system, right? So basically, if you take and move this force couple system to O prime, a certain distance S, you can figure out that moment at O prime by just adding the moment at R, or the moment at O, plus the cross product distance crossed with R, right? And this makes sense, right? This is just a force times a distance, right? And this is a moment. So to get the new moment here, you basically add the new moment, right, distance times force, with the other moment. So let's see, two systems of forces are equivalent if they can be reduced to the same force couple system. So if you can get the same force couple system, then you have two systems of equivalent forces. All right. This is just another scenario. If you have a resultant force and a couple that are perpendicular, mutually perpendicular, you can replace it by a single force acting along a new line of action. So let's see what that looks like, right? So this is going to be applied to a system where either the forces are concurrent, sorry. The concurrent forces are just acting on the same point, right? All the lines of action pass through the same point. Coplanar forces, they all act in the same plane, right? So notice they're not concurrent. They don't all pass to the same point, but they are acting on the same plane. And then parallel forces. So in 3D, if the forces are parallel, right? So notice F1, F2, F3, these two are pointing up in the vertical Y. This is pointing in the negative Y. These are all parallel forces in 3D. All right, so let's see how we're going to reduce these systems. This system of coplanar forces, right, you've got F1, F2, and F3. You can, again, reduce this to a single force couple system, right, the resultant force R, and the moment that the force R exhibits or results in about the origin, right? And this is, again, just the vector math, right? You have the three forces are vectors, and you have distances, distance vectors, position vectors from the origin, and you can come up with a force couple system. You can also, move the line of action, right? So you can take R and you can move its line of action until its moment about O becomes the moment that you're looking for. So you can take a single force, right, and just move it along that line of action until it equals the same moment. And you can see this this distance here, right? Distance MOR divided by R. So that's just calculating that distance. Here's rectangular coordinates. So again, you can see, right, a vector R can be broken into a Y and an X component and a resulting moment from that. If you take now and move that a distance X, right, now you've repositioned that vector. You can see here, oops, yeah, the Y distance is now this original moment divided by Rx. So you've got two things going on. You can move a distance of you can move the distance X, which is Ry. You know, Ry is the one being moved, right? Ry is the perpendicular vector to the axis. And when you move a distance Y, it's Rx is the perpendicular distance. So in rectangular coordinates, you basically have the distance, the X distance times the Y component of the force, minus the Y distance times the X component of the force is the moment. All right, so let's look at the sample problem. There's multiple parts here. For the beam, reduce the system of forces shown to A, an equivalent force couple system at A. So we've got all these forces, and they're acting at different distances from point A, right? So we want to know what's the force couple system at point A. So I think you can realize this can involve knowing these individual distances. And then B, an equivalent force couple system at B. So once we figure out the force couple system at A, we can then move it to B. And then C, a single force or resultant. So what's a single force and where is it? So this sort of will help clarify, I think, these prior slides and what they're talking about. So the strategy here is we're basically going to look at the force part of the system, right, as the sum of the forces. And then the couple part is going to be, okay, where are those forces relative to the point of interest, right? Force times perpendicular distance. That's going to give us the couple. And then once we find that force couple system, we can do parts B and C. We can move it to another point. So if you didn't understand the background slides, hopefully you'll understand the concept from this example. All right, so the first thing is part A. Let's compute the resultant force and the couple at A. So we've got all these forces. We've got 150 acting up, positive J, minus 600, right, negative J, 100. They didn't draw any, obviously this is the X direction and this is the Y direction. Anyway, your resultant vector is just the sum of the forces, right? So we've got 150 newtons J, minus 600 newton J, plus 100 newton J, minus 250 newtons J. Remember, in this textbook and a lot of conventions, a counterclockwise rotation is a positive. If you add these all up, you get a force R minus 600 newtons J, right? So this means the resultant force is negative 600 newtons somewhere, somewhere along this thing. But we want to transfer it over to A. So we're going to put the minus 600 newtons here. And they've already given you the moment, but you can see that the moment, right, at A of the resultant force vector is just the sum of each individual position vector crossed with its own force vector. So what does that mean? We've got a position vector 1.6i, right? This is, I'm assuming meters. Yeah, 1.6 meters, right? Cross product with the minus 600j. Right? So these two, you cross product them. You've got a 2.8i cross product with 100j, right? When you use the vector notation, you can just add these things together. And then the crosses will make the signs work out, right? So like I cross j is going to be positive k, and then, well, I cross j, positive k. Yeah, I cross j. So what do we wind up with here? We wind up with a negative 1880 Newton meter K, right? So that's showing us it's a clockwise direction because it's a negative. So this is the moment about point A. All these forces result in a net force of minus 600 Newton and a moment about A of minus 1880 Newton meter. This is a force coupled system. So we've taken individual forces, we've looked at their distances from the point of interest, and we've created a force coupled system. Okay, so now all we're going to do for part B, we're going to find the equivalent force coupled system at B based on the force coupled system in A. Now, this would be just like as if B was the original reference point, right? So now you've got one force and a moment, right? So the force is completely unchanged. The force is the same. The total net force is just sum of all the forces as before. So we have minus 600 Newton J, except now we're putting it over at B, right? So that's what R is. Now we look and see, okay, how far is B from A, right? And then what's the moment at A? So we have to add, to get the moment at B, we have to add the moment at A to the new moment, which is this force, right, R, crossed with, well, I guess technically it's the position vector, A with respect to B, crossed with R, right? So here we've got the original moment at A, minus 1880 Newton meters K, right? Our I position vector is minus 4.8 meters. Yeah, so this is a position vector of A relative to B. So it's 0 minus 4.8. Remember our original x equals 0 is over here. That's where we get the negative from. And then cross product with the minus 600 newtons, J, right? So you do this math, right? I cross J is K, negative times a negative is a positive, and you wind up with the total moment. The new force couple system is over here. This is the same as minus 600 Newton J with a 1000 Newton meter K couple to it. Oh, here it is. So, yeah, so this is just the force, this is reminding you, right? The force couple system at O may be moved to O prime with the addition of the moment of R about O prime, right? So that's all we did here, right? We moved it from A to B, O to O prime by just adding the original moment to this new moment that's generated by the position vector crossed with the force vector at the new position. All right, finally, part C is the resultant of the given system of forces is equal to R, and its point of application must be such that the moment of R about A is equal to the moment of R at A. So all we're saying here is all those forces that we saw in part A, what's that equivalent to? It's equivalent to applying one force at some distance x from A, right? And we already know the moment about A of the resultant, right? We know this information. This is from part A. It's minus 1880 Newton meter Kelvin. What we're saying here is we have this resultant force. We don't know the distance it needs to be applied at to get that equivalent moment. So this is the equation we're setting up, right? X in the I direction, cross product with the minus 600 NJ, gives us this moment. So you do the math, and you just wind up seeing that if X is 3.13 meters, in other words, you apply this force, minus 600 newtons, in the J direction at 3.13 meters away from A, you will have a single force that's equivalent to the original system, and it's defined as this: 600 newtons downward at x equals 3.3 meters from your original A coordinate. So yeah, the one thing I should probably add to these slides is they weren't very clear about the coordinate system. The whole time they're using x equals 0 at A, just starting from the first part of the problem. So later on, we're going to be using these same principles to find center of gravity, center of mass, things like that. It's basically just, forces times distances.